Hello students, so let us discuss the last concept existing in this chapter is which one it is? Work energy principle, or we can also call it what work energy theorems. So as we have discussed in our previous class, the work is said to be done only when force applied. What it is? Only when a force applied on an object causes it to move to a distance in the directions of what is applied forces. Then only we can say that the work is said to be done. What it is? The work is said to be done only when the force applied on an object causes it to move to a distance in the directions of what is applied forces. Okay. So next, I think this one is work energy principle. So you know that the meaning of energy is the capacity to do the work, and so we know that in the last class we have discussed the law of conservation of what energy, so that one form of energy can be transformed into what another form of energy. It is the statement of your law of conservation of energy is energy is neither created nor it is what destroyed. Uh, the sum of the energy, the sum of all the energy in the universe remains a constant. Energy is always conserved. So when transformed from one form to what another form. So these are the what different ways of your what stating the law of conservation of what is energy. Okay. So here that our work energy principle, what it states, so what the meaning of this work energy theorem is. The work done by a constant force on a particle is equals to the what is a change in kinetic energy of that particle. It means that due to the applications of your what a constant force on that object, which brings a what the change in kinetic energy of that particle. So that's the meaning of what work energy theorem. Work done by a what a constant force on a particle is equals to the what the change in kinetic energy of the particle. So let's derive how that constant force applications of your constant force on that on that particles will will be equals to and what a change in kinetic energy of that particles. Okay, that a constant force F act on a body of mass m. Let a what a constant force F act on a body of mass m and displaces it to a distance of what is ds. So when that your a constant force is what acted on that your body having a mass of what is m. So due to this applications, that body displaces to a what distance of ds in the time of interval what dt in the direction of what forces. Then the work done by your constant force on that your particle is given by we know that dw is equals to what f into ds. So therefore the total work done is given by what is w is equals to integration of what is dw is. The integration of it is what f into ds. So we know that f is equals to what according to second Newton's second law of motion. F is equals to what is ma. So a is nothing but what? So dv divided by dt, the rate of change of velocity is nothing but what it is acceleration. So integration of m into so dv by dt into what is ds. So that's is equals to, so here I am interchanging m into integration of what? So ds by dt into what is dx. Okay. So that is equals to small m ds by dt is nothing but velocity. So that's why. So this equation reduces to what? M m into the integration of what? So v into dv is there. Okay. Suppose if v naught is the initial velocity and v is the what? The final velocity, then w is equals to, this is m into integration of v naught to what? V. So in order to have what amount of work is done. Okay. So for that, so you are integrating what that above quantity between the limit of what v naught to what? V. So where v naught is what? Initial velocity, and v is what? The final velocity of the particle is. Okay. So then after integrations, you are getting v square divided by what? V2 and put the limit v naught to what? V is. Okay. Next, on applying that your limits to that above equations, so we'll get what? W is equals to em into bracket v square by 2 minus of what? So v naught square by what? 2. Or that is equals to what? 1 by 2 mv square minus of what? 1 by 2 mv naught square. So m 1 by 2 mv square is nothing but what? Final kinetic energy. Whereas 1 by 2 mv naught square is nothing but what? Initial kinetic energies. Okay. So the final kinetic energy minus of what is initial kinetic energy. So will give you is designated by what? Del of K. So this is del of Ke is nothing but what? The change in kinetic energy. Okay. So therefore, so that above equations represents that, so whatever we said in the beginning for the what Kennedy principle or the theorem, it is in terms of kinetic energy. So that's what Kennedy principle states that work done by a force is equals to the what? The change in kinetic energy of the what is a body. So whenever a constant force is applying on a particles, that changes and what? It's a kinetic energy inside that is what? Bodies. So that's the theorem of what? Work energy principle. Okay. Thank you.